Hello guys, welcome once more to another video in this YouTube channel. So today we are going to be looking at Public Works Meng 2019 question 2. It reads, let S be a segment of length A and consider all right-angled triangles having hypotenuse equal to S. The locus consisting of the vertices opposite to the hypotenuse of all such triangles is it a line? Is it a segment of length A? Is it a circle of radius A, or is it a finite set of points? Alright, so first of all, we have some key things here to note. S is a segment of length A. A segment is simply a line that has a beginning and an end. Now, S is a segment of length A, and then we are considering something. We are considering all. Mark this word, all. So we are considering all right-angled triangles having hypotenuse equal to S. So we are going to begin with a base case before we construct a set of infinite right-angled triangles whose hypotenuses are all equal to S. So our base case is where we have this right-angled triangle. The line in white is simply our line segment S, and the length of that line, we're told that it is A. Now, the objective of the equation is to find the locus consisting of the vertices that are opposite to the hypotenuse of all such triangles. Okay, so first of all, we have to construct all right-angled triangles whose hypotenuse are equal to S. And then now, from there now, we now look for a locus that consists of all the vertices opposite to the hypotenuse of all those triangles. All right, so constructing all those triangles entails us in just constructing the base and the height, because all those triangles will have hypotenuse equal to S. So it means that if I just construct this other one here, you see that the hypotenuse of this other one here is just S. Okay, so I've just constructed the base and the height. Okay, now we need to generate, or we need to construct other right angle triangles, and then now we find the locus that consists the vertices opposite to the hypotenuse of all such triangles. Remember that in this basic case here, if a vertex is opposite to the hypotenuse, then that vertex must be at the right angle, if you see it clearly. So you see that this vertex here is clearly opposite to the hypotenuse. Even this other vertex is also opposite to the hypotenuse. All right, so now we are going to construct other ones, and then now we try to generate the figure that is formed. So I have another one here where the hypotenuse is S, so I just constructed the base and the height, noting that this is a vertex, is a right angle, it's a vertex that is opposite to the hypotenuse. Now I can construct another one. This is it. I just constructed the base and the height. You see, this is another vertex here that is opposite to the hypotenuse. Remember again, we said we are considering all right-angled triangles whose hypotenuses are equal to S. So it means that the line in white does not change. So I'm just constructing the base and the height of all other right-angled triangles. Okay, so we can go ahead constructing. You see, we can construct, there are infinite number of them. Okay, so we can just construct an n where we have to construct an n, and then we now see the figure that is being generated. Okay, now we now have to represent, we now have to indicate those vertices, because we need to find the locus consisting of the vertices opposite to the hypotenuse of all such triangles. So this is just a case where I've just taken some of the such triangles, okay, and then now let's start indicating the vertices that are opposite to the hypotenuse. Our hypotenuse here is simply the line segment S, whose length is A. So if I want to be indicating the vertices, then I just need to be indicating the vertices at this right angle, at the right angle here, right? Because those vertices are clearly opposite to the line segment S, as I earlier explained. So we are going to have, for the original right angle triangle, Okay, we have that this is the vertex that is opposite to the hypotenuse. Now for this other guy here, this is a vertex that is opposite to the hypotenuse. For this other man, this other one, this is a vertex that is opposite to the hypotenuse. So you see that all those vertices are going to be at the right angle. Okay, so clearly the figure that is going to be formed is a circle. Now in circle geometry, there is a theorem that says that whenever two lines leave the whenever two lines that leave the diameter of a circle meet at the circumference, they always meet at 90 degrees. So you clearly see that this line, this is the diameter of the circle, a line that divides the circle into two equal parts. You see that this line here is leaving the diameter, the end of the diameter. This other line is also leaving the end of the diameter. They meet at the circumference of the circle and they always meet at 90 degrees. It therefore means that since all these vertices are at 90 degrees, then the locus consisting of those vertices will simply be a circle. Now, it is a circle whose diameter is A. Therefore, we can conclude that the locus consisting of the vertices that are opposite to the hypotenuse of all such triangles is either a circle whose radius is A divided by 2, or we say a circle whose diameter is A. So there is no right answer. Thank you for watching and see you in the next video.